All right, next up we have Joshua Hazelnis. I'll let him explain his title. There you go, just that side button.
So it's a pleasure to be here. My name is Joshua Hazelnis, and I'm going to talk about how genes are a possible solution for clean, renewable energy storage. And I just want to start by kind of considering how much do genes really cost? Like if somebody were to ask me that question on how much these genes cost, I'd probably give them the monetary value or how much I paid for them. But if I ask somebody from Sri Lanka, Bangladesh, Pakistan, or India, for instance, they might paint me a different picture because these are where the textile industries are located. These are where the genes are most likely being produced. You see, the chemicals and the dyes that are going into making these jeans and clothing are being dumped into the local waterways and river systems and polluting the environment there and causing physical harm to the people who live there. So, what truly is the environmental cost? Well, 17 to 20% of all wastewater in industry is from the textile industry. And what we find is that from a single pair of jeans, the same jeans in which I'm wearing today even, costs about 2,700 liters of wastewater. That is equal to about 3 years worth of drinking water for the average person. So what about the people who live there? What about the people who are interacting with this water and these chemicals on a daily basis? Well, research shows that, yes, they're likely to develop allergies and skin irritations, but over time it accumulates within the body and more life-threatening things persist, such as cancers and mutations. So what can we do about this? Well, if we look at the chemical composition, we note that there's one chemical in particular, methylene blue. It's the most commonly used dye within the industry, and it's the most found within the wastewater. And that's why it's been one of the biggest topics of discussion and find for the solution. And researchers tried to take it out of the water, but these are very costly and it's really hard to implement on a large scale. So I beg the question, can we reuse the methylene blue containing wastewater? I think that we can, and that is in the form of sustainable, renewable energy. You see, at the center of this solution is the redox flow battery, and I know it seems pretty daunting when you look at this diagram, but really, it's just a battery. One that's both sustainable and scalable. If you look at the external tanks at a simplified diagram of this, you find that the center is where the charging and discharging takes place. But the external tanks, that's where energy storage happens. That's where we can put our solution. That's where we can put the methylene blue containing wastewater. So this was the same question that we asked about a year ago here at the University of Buffalo, under the direction of Dr. Cook and my mentor, Angela. What was concluded was that methylene blue containing wastewater has the ability and potential to store about 2.7 watt hours per liter. For that single pair of jeans, that 2,700 liters that's wasted, it equates to about 7 kilowatts of energy storage. That's enough to be 100% renewable in areas where the textile industry is prominent and places where they can power their homes and businesses when paired with renewable energy. Because what we find is that the redox flow battery is a great pair for renewable energy. Because renewable energy, as many of us know, is intermittent energy production. When the sun isn't shining and when the wind isn't blowing, we find that there's no energy being produced and demand cannot be met. So we can essentially pair these methylene blue containing wastewater redox flow batteries with renewable energy and set up what are known as microgrids, grids that are solely running on their own energy production, independent from the current infrastructure and electrical grid that's there, that uses fossil fuels and CO2 producing agents that contribute to global warming. So what I'm proposing is we can solve two problems here. we can not only manage the wastewater of the textile industry that contains chemicals such as methylene blue, but we can also use it as renewable energy storage that can set up microgrids independent of the current infrastructure and move our dependence away from fossil fuels. Thank you.
Questions from the judges?
Thank you very much. So my question is around, where you would think of using this technology. Is this technology, do you think of using in the States? Do you think of using, obviously you were showing some pictures in terms of developing countries, but I'm curious how much fuel, if you will, now that I'm thinking of jeans as fuel, how much is there and how much can we look to this as something that could scale?
Well, that's a great question, and I think that's really important to consider when we're trying to implement this idea. And I think that when we think of how much fuel is there, the wastewater is essentially our fuel. This wastewater is a heavy, heavy pollutant, and anywhere where the textile industry is prominent, it's being produced and it's acting as a pollutant to the environment and the river system. So I would argue there that that's an excess, and that wouldn't be a limiting factor. As far as implementation and where this would be used, we kind of have to go and look towards the energy usage in certain areas. So if we look back to where I was saying India and things like that, where textile industries are most prominent, we find that it has a very low energy usage per household for kilowatt hours. But if we double that to the States, we find that it's almost 10 times as that. So not to say that this idea wouldn't work within the States, it just means that we would have to focus a little more research on making this solution a little more concentrated, so that way it has better energy storage capabilities, so that way we're not storing it in large excess, but on a smaller scale. But this would be great where the textile industries are prominent.
How long can the battery operate? Like, what's the byproduct and the longevity of this?
For this current system right now, we have had proof of concept as far as being able to show that it has electrochemical properties and it can potentially do this kind of application. As far as cycling ability, compared to other systems with the redox flow battery, you can have up to thousands of different charge and discharge cycles. And the only maintenance that would be required is changing of what's known as the electrodes in the membrane, which are very insignificant as far as cost goes. And so what we find is that the solution isn't then obsolete. We just simply replace the solution, and we can either replenish the solution and put it back into electrochemistry applications, or have it as a buffer zone, because then we can then implement it into different cleaning techniques.
It's funny, I do work with Methylene Blue from an absorption perspective, and I never view it as an energy source here, but I'm getting my head around this. So what are you actually turning the Methylene Blue into? So presumably this is, the motivation was it would remove the Methylene Blue problem. So what is it being changed into as a result of this battery process that's actually removing and cleaning the drinking water or the water sources? So that's part A, and then part B is there an energy demand associated with this process? So you had membranes. Membranes often mean there's pumps involved. Pumps mean energy consumption and things like that. And so 7 kilowatt hours is great, but that's, at the same time, it's not that big of a number. I mean, that's a few light bulbs a day are 7 kilowatt hours. So So anyway, those are deep technical questions, so maybe...
Sure. So to address that, I think that, for one, you were saying methylene removal and things like that. As far as that goes, we're not using methylene blue as a removed product. That's kind of the benefit of this method, is being able to use the current state at which it's in with the waste product and using that within our battery. So there's no processing that's going to be required in order for it to be applied. As far as what is going into it, as far as energy intensive and things like that, there is definitely pumps required to push the flow but really the economic value of this, and what we look at is the electrolyte solution where the cost is, that's the wastewater. And we're really going to get a return on investment. The energy that's put into the process And the 7 kilowatt hours number, the 7 kilowatt hours number is significant in that it's doubled with the energy production. That, alongside the renewables, is just helping to meet the demand, that gap that we're not getting with our renewable energy. And so I think as far as energy goes being put in, we're essentially getting that energy back twofold, because we're getting our investment back economically, and we're also getting our energy back as far as the process and what's going into it.
Really quick, just
Sure.
So, is there any adverse effect in terms of the synthesizing that's taking place to get that energy storage that makes things worse? In other words, right, you're using a pretty toxic substance, or a substance that has consequences. Are we, through those reactions or through any of that storage, does anything come out of it more toxic than went in?
Fantastic question. And I think that when we think about when we're putting it into the battery is a closed system. These are going to be contained in tanks that are not going to react in any way with the product. The simple reaction that's taking place is just an electron transfer. So we're not changing the chemical properties per se of the chemicals that are going in, but rather just transforming it in a way that meets our needs of energy consumption. So in that case, it's not going to be any more toxic or any more harmful to the environment, and it's going to be totally closed and contained throughout the entirety of the process. You're welcome.
Thank you, Josh.
Thank you.